Hi, welcome back. This is lecture 10. Today we'll prove V rings are valuation rings. Remember last class we proved that valuation rings are V rings. So today we'll be proving the converse. So lecture 10. So the topic of today's lecture is that we want to show that V rings are valuation rings. So given a V ring, how do I put a valuation on it? So let B be a V ring with fraction field K. So now to define a valuation, I need a totally ordered abelian group. So let's try to find a totally ordered abelian group associated to this situation. So the eventual punchline is that this totally ordered abelian group will be K cross mod B cross. So I want to take this abelian group and I want to put a total order on this. It's compatible with respect to the group operation, which is multiplication. So take two coset representatives alpha and beta in K cross mod B cross. And my definition, so I'll just define this order that alpha is larger than equal to beta if for some lifts alpha and beta of the square bracket alpha square bracket beta, what we have is that the ratio alpha over beta belongs to B. Okay, this is just a definition, and the first thing that I want to check is that this definition doesn't depend on this choice of lifts alpha and beta. So the definition of this order does not depend on the choice of lifts alpha beta of the square bracket alpha square bracket beta respectively. And why is that true? Suppose you take two other lifts, let's say alpha 1 and beta 1 are also lifts of square bracket alpha and square bracket beta respectively. So then how does alpha 1 relate to alpha and how does beta 1 relate to beta? We're looking at K cross mod B cross. So two lifts of the same element will differ by a unit in B. So alpha 1 is alpha times U1 and beta 1 is say beta times U2 for some units U1 and U2 in B cross. Okay, so in particular U1 and U2, since they're units in B cross, their inverses will belong to B. Okay, so then, well, alpha 1 over beta 1, that equals alpha U1 over beta U2. And so you can just rewrite this as alpha 1 U2 inverse times alpha over beta. And then you see that U1 belongs to B, U2 inverse belongs to B. And if the square bracket alpha is larger than equal to square bracket beta, this means that alpha over beta belongs to B. And so in this case, this will also belong to B if square bracket alpha is larger than equal to square bracket beta. And so what we have is that if square bracket alpha is larger than equal to square bracket beta, then square bracket alpha 1 is larger than equal to square bracket beta 1. And so this proves the claim. So the definition of this order does not depend on the choice of lifts of square bracket alpha and square bracket beta. And so henceforth I'll just suppress this choice So I'll just suppress this ambiguity in the choice of livs or choice of representatives of square brackets alpha and square brackets beta. And so sometimes I'm just not going to say square brackets, I'm just going to say alpha and beta if it's clear from context. Okay, so now the next proposition. So I have k cross mod b cross. So the group operation is multiplication, and then I've tried to define an order which was this greater than equal to. So the next proposition is that this is a totally ordered abelian group. Okay, so this group operation is given by multiplication. This is induced by the field multiplication of the field K. Okay. So proof, well, clearly K cross is an abelian group, so this quotient is an abelian group. Now I have to check that the symbol greater than equal to defines the total order. That's our first claim, is that greater than equal to defines a total order on K cross mod B cross. And so this proof of claim, so you take two elements, square brackets alpha and square brackets beta in K cross mod B cross, and choose appropriate livs alpha and beta. So what do we want to show? So given these two elements, we want to show that they're comparable. So either alpha is larger than or equal to beta, or that beta is larger than or equal to alpha. Okay, and again I'm just omitting saying square brackets. Again, just rewriting this, that is, we want to show what does it mean for alpha to be greater than or equal to beta. We want the ratio alpha over beta to belong to B, or we want the ratio beta over alpha to belong to B. But this follows from the definition of a V ring. Since alpha and beta, these livs, belong to K cross, and hence alpha beta is not 0. And so by definition of this property of B being a V ring, we have either alpha beta belongs to B, or its inverse belongs to B. And what's the inverse of alpha over beta? It's beta over alpha. Okay, and that's exactly what we wanted to show. We wanted to show that either alpha or beta belongs to B, or beta or alpha belongs to B. And so this just follows by unwinding the definition of what it means for B to be a V ring. Okay, so this proves claim A. And so for the next claim, this greater than or equal to is antisymmetric. So again, what does that mean? So suppose I take two elements alpha and beta, the property that we have alpha is larger than or equal to beta, and beta is larger than or equal to alpha, that is, this ratio alpha or beta belongs to B, and its inverse beta or alpha also belongs to B. So let's call alpha or beta as R, and let's call beta or alpha as S. Okay, and what do we want to show? We want to show that the square bracket alpha and square brackets beta, they are equal to each other. Now, what do we have by hypothesis? We have that alpha or beta belongs to B and beta or alpha belongs to B. We call them R and S. So if you look at the product R times S, this is nothing but alpha or beta times beta or alpha, which is just 1. So you have two elements R and S in B, the product equals 1. So this means that R and S are units in B, and in particular R comma S belongs to B cross. Okay, so this just means that alpha or beta belongs to B cross. So in alpha and beta define the same coset representatives in K cross mod B cross, since the ratio belongs to B cross. Okay, so we've shown, and this proves claim B. So the next claim is that the symbol greater than equal to or larger than equal to is transitive. So again, proof of this claim. So take three elements, say alpha 1, alpha 2, alpha 3 in K cross mod B cross with the property that square brackets alpha 1 is larger than square brackets alpha 2 and square brackets alpha 2 is larger than equal to square brackets alpha 3. And again, what does it mean unwinding this definition of this greater than equal to? It means that if you choose lifts alpha 1 and alpha 2, the ratio belongs to B, and if you choose lifts alpha 2 and alpha 3, the ratio alpha 2 over alpha 3 belongs to B. Okay, and so now if you multiply alpha 1, if you look at the ratio alpha 1 over alpha 3, and if you just divide and multiply by alpha 2, you get alpha 1 over alpha 2 times alpha 2 over alpha 3. But the first term of this product, alpha 1 over alpha 2, belongs to B, and the second term of this product, alpha 2 over alpha 3, that also belongs to B. So you're multiplying two elements in B, so the product also belongs to B, since B is a ring and closed under multiplication. So we have that alpha 1 over alpha 3 belongs to B, and by this definition it means that square bracket alpha 1 is larger than equal to square brackets alpha 3. And so this proves claim C, since we've shown that the symbol greater than equal to is transitive. And the last property that we need to show is that the symbol greater than equal to is compatible with the group operation given by this field multiplication. So it's compatible with this field multiplication. So let me call it the group operation on K cross mod B cross induced by field multiplication. So suppose once again you have square brackets alpha, square brackets beta in K cross mod B cross with the property that alpha is larger than equal to beta, and you take some random element, let's call it delta, square brackets delta in K cross mod B cross. Now again, what does it mean for alpha to be larger than or equal to beta? It means that you choose lifts of the square bracket alpha, square bracket beta. You take the ratio alpha over beta that belongs to B. And now what do we want to show? That if you multiply delta with alpha, you get that that's larger than or equal to delta times beta. Okay, but now again, this is just unwinding definition. Since alpha over beta belongs to B, well, what about alpha delta over beta delta? This is nothing but alpha over beta. And so this is just, by hypothesis, this is in B. Okay, so this means that square brackets alpha delta is larger than or equal to square brackets beta delta. But this is just alpha times delta is larger than or equal to beta times delta. Okay, and so this proves the claim. And combining all these claims, what we've shown is we've proved the proposition that K cross mod B cross with its group operation induced by field multiplication on K with this ordering that we've just defined is a totally ordered abelian group. And so now moving on to describing a valuation on K cross from this V ring B. So suppose B is a V ring inside K. Then we have this natural projection map from K cross to K cross mod B cross, and the claim is that this defines a valuation on K. Okay, and again, just reminding you what does that mean? That is, you need to show that it has this map pi has two properties. Pi of alpha beta is pi of alpha times pi of beta, and if you have alpha beta in K cross with the property that its sum is not 0, then pi of alpha plus beta is larger than or equal to the minimum of pi of alpha and pi of beta. Okay. The second property is what we called the ultrametric property. And I've used this fancy symbol pi, but just remark from the previous definition, pi of alpha is also what I denoted square brackets alpha. Okay. So now the proof of this proposition, A follows, the first property follows immediately because pi is just a natural projection map. So it's this natural map given by quotient of abelian groups. Since pi is a natural quotient map of abelian groups. And so in particular, it's a group homomorphism. And so pi of alpha beta, because it's a group homomorphism, it's pi of alpha times pi of beta. Now to prove part B, again, assume without loss of generality, I have two elements, pi of alpha and pi of beta. So without loss of generality, assume that pi of alpha is larger than or equal to pi of beta. And again, what does that mean? By our notation, this just means that square brackets alpha is larger than or equal to square brackets beta. And again, what does that mean? That just means that alpha over beta belongs to B. Okay, so again, this minimum of pi of alpha and pi of beta in this case is just given by pi of beta. Now, since by assumption alpha plus beta is not 0, and also beta is not 0 because it's in K cross. So I have alpha plus beta, but if I just factor out the beta, I get beta times alpha or beta plus 1. And so if I look at alpha plus beta divided by beta, this is alpha or beta plus 1. But one of our hypotheses is that alpha or beta belongs to B. So this first term out here belongs to B. B is a ring, so 1 also belongs to B. So you're adding two elements in this ring B, so the sum also belongs to B. So this ratio alpha over beta belongs to this ring B. So by the definition of our order, alpha plus beta is larger than or equal to beta. And so just unwinding the notations again, the square brackets alpha plus beta was just pi of alpha plus beta, and the square brackets beta, by our choice of beta, was the minimum of pi of alpha and pi of beta. So this is nothing but pi of beta, and by our choice of beta, this was this minimum of pi of alpha and pi of beta. And so this proves property B. Or this establishes property B. And hence this completes the proof of the proposition that the natural surjection from K cross to K cross mod B cross is a valuation if B is a V ring. Okay. So if B is a V ring, we have a natural valuation to consider, and if you have a valuation, one natural ring that we can consider is this valuation ring. So I have this valuation, and we consider this valuation ring for that, which we call OK pi, and we can ask how is it related to B, and the next proposition is that this equals B. Okay, so remember that the valuation was taking values in K cross mod B cross, so I'll let gamma denote K cross mod B cross. And what was the identity element of gamma? Well, this is the identity element of K cross mod B cross, where the group operation is given by field multiplication of K. So this is just this element 1, the image of 1 from K cross. So just a remark that we're switching between the additive group notation if I use gamma and the multiplicative group notation on K cross mod B cross. So it's just a matter of notation, but sometimes I'll use, so far I've been using the multiplicative group notation, but if I want to use the gamma, I'll try to switch to the additive group notation. Okay, so note that if you have an element of B, let's call it little b that's not 0, then its valuation is larger than or equal to the valuation of this identity element of gamma, which was this element 1 bar. So let me just call 0 gamma as 1. And so why is this the case? Because the ratio. So what does it mean for an element B to be larger than or equal to this element 1? It just means that the ratio should belong to B, but the ratio is little b over 1, which is B, and that belongs to the ring B. So every element of this ring B has valuation larger than or equal to this identity element of gamma. So this means that we get this one-way inclusion that this ring B sits inside OK pi, which, let me remind you, was the collection of all elements in K cross, such that its valuation is larger than or equal to the valuation of the identity element along with the 0 element of B. Okay, so we get one inclusion. Now similarly, if you have an element alpha that's not 0 and that's in OK pi, again if you're in OK pi, that means that your valuation is larger than or equal to the identity element, which means that alpha over 1 belongs to B. So alpha belongs to B, so this, if alpha is not 0 and you're in OK pi, then that means that alpha over 1 belongs to B, so alpha belongs to B. But if alpha is 0, is a 0 element of OK pi, then also you belong to B because B is a ring and it contains 0. So in either case, what we have is the reverse inclusion, that the valuation ring OK pi sits inside B. So combining the two inclusions in the blue boxes, we get equality. Thus we get that B is in fact OK pi. Okay, so this proves the proposition and the upshot is that if B is a V ring, it can be recovered as the valuation ring of the natural induced valuation pi from K cross to K cross mod B cross. So in this sense, a V ring is also a valuation ring, and in the last class we showed that a valuation ring is a V ring. So from now onwards, we'll use these two terminologies interchangeably. So we'll use the terms V rings and valuation rings interchangeably. Thank you.